The sun is so bright that it hurts to look at it directly. However, we know that the sun is a star and that there are countless stars in the sky. So why is the sun so much brighter than them? Well, duh, you might think that's an easy question to answer. Distance. But diving deeply into the science and math of the situation can help us understand more complex systems. So yes, the one-word answer to this question is distance. While the stars in the night sky are lanterns seen from a distance, the sun is a flashlight held right up to your face. Just like with the volume of sounds, we have an intuitive sense that closer sensory experiences are more intense than farther off ones. This intuition is backed up by some simple science and geometry. Let's take a 25-watt light bulb as an example. Light contains energy, so we can describe a certain amount of light as a certain amount of energy being transferred through space. For those unfamiliar, a watt is a unit of power, or energy over time. So a 25-watt light bulb is a constant source of 25 joules of light being emitted into space every second. What makes this bulb a good model for a star is that, like a star, it releases light in just about every direction, distributed roughly evenly throughout space. Thus, the 25 watts of power are equally spread out as they travel out into space. So, if we looked at all the photons that left the light bulb at the same time, we would see an expanding sphere of light moving outward into space. Think about what that means for the individual photons. In 1 second, a 25-watt bulb releases about 6.25 times 10 to the 19 photons of visible light, which may sound like a lot, but remember that photons are on the same scale as electrons, and there are about 10 to the 28 electrons in the human body. If all these photons were evenly spread out over a sphere 1 meter in radius, then the average separation between photons would be the square root of the quantity 4 times pi times 1 squared divided by the quantity 6.25 times 10 to the 19, or about 447 picometers. Once the light gets up to 2 meters from the bulb, the same formula, dividing the surface area of the sphere by the number of photons in it, yields an average separation of 894 picometers. At 10 meters, the photons would be separated by an average of 4.47 nanometers. As you can see, the photons get farther apart from each other as they get farther from their source. This is like stretching out the sphere of light and thinning it in the process. Now you may be getting a sense of why light dims as it travels through space. A more useful metric than discrete photons and average separations for determining how bright a source appears is the concept of irradiance. Irradiance flips our previous equation on its head and replaces photons with the amount of energy they carry. Also, irradiance is a rate, so it uses joules of light per second rather than total joules of light. Irradiance is thus measured in watts per square meter, or how much energy strikes 1 square meter in 1 second. So we can take our 25 watts of power and spread them over the 12.6 square meters of our 1 meter radius sphere, giving us an irradiance of 1.99 watts per square meter. Quick side note, if the irradiance of a 25-watt bulb from 1 meter away is 1.99 watts per square meter, then what's the irradiance of the sun from 150 million kilometers away? Well, it's about 1370 watts per square meter. No wonder it hurts to look at. Anyway, at 2 meters, the irradiance of the bulb is 498 milliwatts per square meter. Why such a drastic drop-off from 1 to 2 meters? Well, the value of irradiance follows something known as the inverse square law as distance increases. If the distance doubles, then the irradiance drops by a factor of 4. If the distance increases by a factor of 10, then the irradiance drops by a factor of 100. This relationship can be explained by our irradiance equation. Since the bulb's wattage, or luminosity, is constant regardless of distance, it doesn't matter where you are, a 25-watt bulb is still a 25-watt bulb, the only changing factor is the surface area of our imaginary sphere. Since the surface area of a sphere is proportional to the square of its radius, when we divide by surface area, irradiance is proportional to the inverse square of radius. Hence, inverse square law. Now the difference between the sun and the other stars in the sky is clear. The other stars in the sky are so far away that their luminosities are diluted by the vast gulfs of space between us. In fact, the vast majority of stars in the sky are thousands or millions of times more luminous than the sun in terms of total wattage. It's just that the huge distances to those stars lowers their irradiances through the inverse square law. Let's take a look at the brightest star in the sky other than the sun, Sirius. I put star in air quotes because Sirius is actually two stars in a binary system. However, it is so far away from us that it appears as a single dot to the human eye. So, what is the combined luminosity of Sirius A and B? 25.5 times that of the sun, most of that coming from Sirius A. But Sirius is 8.71 light years away, 551,000 times farther from Earth than the sun is. Thus, the irradiance of Sirius is 11.9 billion times less than the sun's, or about 115 nanowatts per square meter. And that's the brightest star in the night sky. Naturally, these huge differences in irradiance become difficult to talk about. It's just not a very human scale to talk about factors in the billions. Thus, astronomers have come up with the apparent magnitude scale. Like the decibel scale or the Richter scale, the apparent magnitude scale takes values that fall over a broad range of magnitudes and condenses them by taking their logarithms. For the apparent magnitude scale, that is -2.5 times the log base 10 of irradiance. Thus, very bright objects have very negative values, and very dim ones have very positive values. Instead of 11.9 billion times dimmer than the sun, Sirius can be described as 25.2 magnitudes more positive than the sun on the scale. Most of the stars visible in the night sky, by the way, cluster around magnitudes -1 to +5. So the sun sets itself apart at -26.7. Here is a list of the 10 brightest objects in the sky and their apparent magnitudes. Notice that the top 6 of them are all objects in our solar system, and of the top 10, there are only 3 stars besides the sun. Strange how mere planets can outshine entire stars. That's the power of the inverse square law and a reflection of the true scale of interstellar space. Tune in next time, where we'll talk about calculating the apparent magnitudes of planets.